nodes. We know that in control we have three different nodes, three most important nodes. One is config node, second one is control node, and third one is analytics node. So all these nodes has different function. And use the control troubleshooting. Wow, that is very big topic. I remember yesterday, I don't know who asked me the question. In the old day, we troubleshooting by using the command, right? Now in control, how do we troubleshooting that? Because they will generate the alias label automatically. They will learn the route, teach the route automatically. If there's anything wrong, how do you check troubleshooting? So that's a problem. We need to understand the troubleshooting, the different methods of the troubleshooting. So go to the control. Two main components, control controller, control V router. Actually, V router is in the compute node. And when we talk about the control and orchestration system, so control by itself is a controller. It will talk to the OpenStack by using the northbound. Again, what is the northbound protocol?
Northbound protocol, netconf.
No.
Oh, northbound towards the REST API.
REST API, right? Okay. Yeah. And this is the slide. We have seen it several times, so I skip it. OpenStack in here. And then you would like to configure it. You are in here. You can use different way. API, okay, you can use the API by talk to the OpenStack different project. And one of the project in here is your context window, right? Hit. You define two files. Again, what are the two files? Hot. YAML. Yes. All right. And then you provide all the parameters from to here, and it will translate that information to a language and sending to here. And then it will talk to the control by using vendor specific API. So which means the REST. So, REST. That is the northbound, because we talk about northbound is from the control point of view. What is the northbound? And in control, in order to talk to the OpenStack, there are so many projects, and one of the projects will be responsible for the talking to control. So what's the project name? It's on the slide. Neutron. Okay, so control has a neutron in here, and there is another neutron over there. This is control, but some other vendor, for example, Cisco, for example, the other vendor like VMware, they also has their own add-on or plugin, so they can talk to the neutron.
Do you know what Cisco's one is called?
I don't know, but there is a neutron plugin in their products.
Oh, okay.
Yeah, you call this neutron plugin. Okay, so they plug in a small software in their product, so they can use the northbound protocol to talk to the OpenStack. Okay, and then we also supporting the container. Again, if you would like to spin up the virtual machine, that is a container. Then in the virtual machine, you don't have to use the hypervisor. Instead, you use what? You use the Docker engine, right? A Docker engine. And your Docker engine will talk to your OpenStack. And your OpenStack will have to talk to your Docker engine by using the the protocol that is XMPP. Okay, now let me skip some of this because this is only the concept of the Docker. You can put Docker in the whole system, and you can have a physical network card connect to the network. So your control device, for example, this is a compute node. You have a virtual machine in here, and there is a container over there. They can always talk to each other by building a tunnel between them. All right, let me pause in here. When I explaining about the control concept, I said that control controller by itself is a round reflector. You know who generated this idea? The guy. We acquired the company, we invited come back to Juniper, right? The name of the guy is called Compella. And he was the author of the RFC and to use the BGP as the signaling protocol. So he was good. He is good. Okay? He is really good. But you know what? He's some kind of, I don't know how to say that, but since we closed the door, he's our vice president right now, but he's some kind of geek. He very focused in a very small room and doing his own things. From my point of view, he's not a guy who very good at interact with the others. Okay, so when one day we have an event, we call it tech event in Korea. So everybody in Juniper employee or engineers all went to attend that event, and he is one of the speakers. So he go to the front stage and speak about the control. And when he talk about the control, he make a joke. He said, "Oh, no, control is something like centralizing. So if you don't centralizing, you will manufacture a very poor product like the Korea car." Everybody is from Korea. And I was, oh my God.
So no one laughed.
Nobody laughed.
No, I would have laughed. I would have had a good time.
Yeah, wow. He's that guy. He's
Yeah.
that
No
kind of
filter.
guy.
It
Yeah.
doesn't have the filter.
Yeah, no filter, yes. And he just think about anything, just split out. Okay, but he used but his technology is really good. So he used to generate the BGP, that is routing protocol, RFC, right? So he used the concept from the BGP to cloud. So let's comparing with this. In the service provider core network, traditionally, you use the PE router connect to the customer CE. Internal goes through the P router, and there is another PE router connect to another customer. Okay, and internally, in order to solve the problem of the full mesh, then you can use the route reflector. So the PE only exchange the route to the route reflector, right? That's the very basic concept. So this concept is from the core of the service provider. He borrowed the concept to control. Then you see, control controller by itself. There are three different nodes. Again, one of the nodes we call it control node, which is not in here. Another node we call it controller node. And the third node we call it analytics node. So we have analytics in here. We have control node in here. That is control node. And then the control node talk to the server with a hypervisor. There is a vRouter. Talk to the server over there is a vRouter. And you see, vRouter is similar to the PE, right? And internally, they are not able to exchange the route by using the traditional BGP protocol, like the IBGP. So they borrow another protocol, they use that as an XMP. And the controller by itself is actually the route reflector. You see, what's different? No difference. So they borrow that. So you can centralize all the control in here. That is your SDN controller, or we call it control. And the difference is in here. In the traditional service provider core, you will build up a tunnel. The tunnel, normally we call it LSP, label switching path, LSP. But you build up the label switching path by using signaling protocol. What kind of the signaling protocol we are talking about? We're talking about traditional LDP. Or if you would like to do the traffic engineering, then you might want to use the RSVP. Or there is a protocol, BGP itself can also be the signaling protocol. So when we talk about signal, why we use the term signal? Signaling means you use a protocol to exchange the route, and then based on the route, you generate the MPLS label. Okay, so as long as you can use any of the protocol to exchange that information and generate the label, that protocol called signaling protocol. So we have LDP, RSVP, or BGP in service provider core. But now, in here, we build up the tunnel. The tunnel is going to sending the traffic through the tunnel by different customer or different tenants. So which means we need to identify each other. So how do we identify each other? One of the way is we use the VXLAN. VXLAN, inside of VXLAN there is a header, we call it VNI, we already know that. But what if you have a device which is a server, the server doesn't have the capability to build up the VXLAN tunnel. So what would you do? Then there's another way. We use MPLS over UDP, MPLS over GIE. So when we talk about the MPLS, which means somebody need to generate a label. So the customer red has a label. Customer green has a different label. So if you're using the MPLS over something, MPLS label will be used to identify tenants. If you're using the VXLAN, the VNI will be used to identify tenants. And then, since you need to build up the tunnel and you need to first tell the device what is the label to identify the customer, who is going to generate the label? Again, that will be the controller. And who is the controller? That will be the control. Okay, so control playing a role like the route reflector. All right, so here, eventually, if you have an environment in your data center, you have open stack, you have controller, and you have multiple computer node over there. Right, now, here's a case. It's a very interesting case. You're Telstra, I'm your customer, I'm Telstra customer. So I know Telstra providing the public cloud, like Amazon. So I go to your browser, I go to your website, and in the website, I want to purchase some of the VMware. I want to purchase some of the virtual machine and build up the network only used by myself. So I'm using your public cloud to create an environment to save my sensitive database or sensitive information. So how do you call that? Virtual private cloud, right? Now I would like to use your public cloud to create an environment that is only save my sensitive information. That is VPC, virtual private cloud. And the topology inside the VPC, I would like to look like this. Okay, I have two subnets. One subnet is green, probably 10.1.1.0. And on the subnet, I have 3 virtual machines. This virtual machine, let's assuming that is SQL database. And there is a firewall virtual machine connecting to another red network. Let's say that 20.1.1.0. Okay? In 20.1.1.0, we have another 3 virtual machines, but these 3 virtual machines are the web server. As the customer, I want to use this web server as the front end. So my consumer can go to my web server, purchase something from my company, but the database will be saved in the SQL. In order to protect the database, I want to put a firewall. So this is my front-end server. I want to provide it to my consumer. And my consumer is from the internet. So internet is physical network, will come to your data center and reach out to one of your virtual routing instance. Based on the routing instance, forward the traffic to the web server, purchase something from me. And then I will save that information to the SQL database. So this is my topology. I want to create this in Telstra. So how do I do that? And then we need to know how it works in very, very detail. So let me skip up this information. This is talk about the project, so we don't have to cover that again. Let me skip some of the slide in here, and please move on to page 31. 31. I know a lot of slides skip, but trust me, this slide will be very interesting. Yes, Steve?
Oh, that's right. I'm a little bit colorblind, so when you said red, I can't see which one's red.
I'm colorblind. Yes.
You're colorblind?
Yes.
Oh, you're saying that looks pink to me.
Oh, yeah. Sorry, so that's my fault, not your fault.
Oh, okay, yeah.
Yeah, I'm colorblind.
Which colorblind? The red, green?
I have difficulty to distinguish between the pink, red, and green.
Yeah, same.
So if you walk on the street, if I see the traffic light, I don't know what is that, so I just follow everybody.
Oh, really? Okay, yeah. I can see the traffic light. What I found is, if I look at the center of the traffic light,
Yes.
it looks bright red, maybe orange.
Yeah.
But if I look at the black part of the cone, the reflection of light, it's very red.
So no worry.
Yeah.
That is me.
But how do you drive then?
Or you just stop when it looks either amber or red.
You know, if you see the traffic sign, the red, the green, it always has their position, right? So when I take the test, I just look at the position.
So you're quite bad colorblind then. It's quite strong colorblindness.
Not very strong,
Oh.
but I shouldn't pass the drive license.
Oh no,
exam.
I passed
shouldn't.
that because I could still see the
I
color.
shouldn't pass that, but I lied to them.
No, but the test they give you with the colors, that doesn't look like the colors in real life. It's
I
easy,
know.
you go, that's
I
easy.
know, it's a color plate, right?
Yes,
Yeah,
oh,
so
yeah,
many
what comes
dots
out
over
was
there.
Yeah, but then in real
You know,
life,
in Taiwan, every young man need to have the army service. So before they get into the army, they will have to be tested by that. So when first time I went to that plate, and the doctor asked me, "What is that?" Everybody said, "5, 5, 5."
Oh, yeah, yeah.
Everybody said, "Oh yes, 5."
and you can't see anything.
Because everybody said 5, yes, 5. Definitely that's 5. But when everybody went out, and the doctor showed me again another plate, I said, this is something I haven't seen it before. Yeah. So
You got caught.
yeah, I got caught. Yeah, no worry. Okay.
But you can fix
That's
that.
me. So if next in any of the slide, if I say that is red color, and it's actually not.
So you
So
guys
don't
what
blame
color is that? Red. So pink.
The arrow is red. The arrow, the up arrow and down arrow.
Yeah, well, they look like different colors, but I wouldn't be able to tell you which colors they are. I think the one going down looks
The
green.
arrow and the box next to it.
Yeah, completely
If
different.
currently if I see my pad, I know there are different colors, but I can tell. But in here, I know this color is a little bit darker, but if I in my pad, I can tell which color is which color.
If the background was black, I could tell it easily, but as soon as you put a white background something, it's hard to tell. It's contrast.
No work. I still alive. Okay, now I have two compute node, compute 1, compute 2. And I have a controller in here. Remember, inside of the controller, you have a control node playing a role like round reflector, right? Now, let's start it from the scratch. If on the right there is a virtual machine B, you just spin up, and then this virtual machine B will receive an IP address from the DHCP server. You know what I mean? You did the lab yesterday, right? DHCP server assigned an IP address which is 10.1.1.2. The DHCP server, which is the vRouter itself, the vRouter will say, there is a route directly connected. So first of all, I will generate that IP address 10.1.1.2 to my logical interface of the vRouter in my routing table. And I consider that is a direct route. And then I'm going to sending the route to route reflector. So first, this route will be sending to route reflector by using what? XMPP. And this route will look like this. I have a directly connected route with next hop 192.168.10.1. And I have already generated a label that is 17, MPLS label I'm talking about. And what is the IP address? 192.168.10.1. That is the physical network count of the compute 2. Okay, so you see the IP address. So I'm sending the route by using the XMPP. So let me put the number 1, sending to the route reflector. The route reflector will reflect the route, so which means send it to another vRouter by using the XMPP. So the route will be reflect from here to here. Then you see nothing changed. IP address 10.1.1.2. Next hop 192.168.10.1. Label 17. Okay, wait a minute. When I receive the direct route, I generate the route with this. The label is 17. The label is generated because of this customer. The customer, can I say that red customer, okay? Red customer has a label of 17. So I send that route to the other compute node. The other compute node, by receiving that route, will first send it to a VRF. So considering that this is a vRouter, and inside of vRouter, for the customer red, we create a VRF, a routing instance. So VRF has the routing table only for the customer red. So I'm going to receive that route, saving to the routing table in here. So that is here. Oh, I have received the route 10.1.1.2, next hop 192.168.10.1, which is the IP address of the compute 2, physical IP address. And the label is 17. After you receiving that, now VMA say, all right, I would like to ping. I would like to ping to 10.1.1.2. Oh, what do I do? I look at the forwarding table. In order to reach out to 10.1.1.2, I need to go to 192.168.10.1. Actually, I need to go through tunnel. And before I sending the traffic to the tunnel, I need to encapsulate the traffic to identify this traffic is going to go to the red customer. So the label should be 17. So the traffic starting from here will look like this. If I'm talking about the ping, everybody knows that ping is an ICMP packet. How do we know that is a ping? Inside of the ping, there is a type and a code. If you are talking about the request, ICMP echo request, the type is 8, code is 0. Okay, no matter. I know ICMP itself will identify that is a ping, it's an echo request. And the traffic will be encapsulated by the IP address. Now, in this case, what is the source address? What is the source address in here? So source address definitely will be 10.1.1.1, right? Destination is, I'm going to pin where? 10.1.1.2. So I'm going to pin to the right side. But since this traffic will has to go to the tunnel, so where is the tunnel? Tunnel will be built from here and all the way to the other side. So when this traffic sending to the tunnel, some of the header will append. So it will look like this. The original traffic, the payload is the ICMP with the type 8, code 0. And the source address is 10.1.1.1. Destination address is 10.1.1.2. Now, since I have to match with the route in order to know how to reach out 10.1.1.2, so first of all, I need to encapsulate with a label. So the label will be the MPLS label 17. And since we need to send this traffic into the tunnel, so I need to encapsulate with a GRE tunnel in this case. We have multiple choice, but let's say that is a GRE. So we have a GRE header, by default is 4 bytes. And then encapsulate with an outer IP header. Now this time, the outer IP header will be the tunnel source and the tunnel destination. So tunnel source in here will be my physical IP address in compute 1. That will be 172.16.10.1, and the destination will be another compute node's IP address. So that will be 192.168.10.1. So this is the tunnel source. This is the tunnel destination. Inside the tunnel, we use the GRE. Inside the GRE, we use an MPLS label. MPLS label will be used to identify this traffic is going to which customer. And then in the payload, we have the original VM source and the destination. And here is the P, right? So the traffic will all the way go to the tunnel and reach out to the other side. When the other side receiving that traffic, the other side will based on the route. So, oh, you are going to, based on the route, there is a route is directly connected, not showing in here. Oh, you are going to destination is 10.1.1.2. So in this vRouter, I will remove all the header and sending the payload to this device. Okay, so that's how it works.
So label 17 for the red customer and label 39 for the green customer.
Yes. In this case, yes.
Okay, so the source and destination IP address, that's the physical network card at the start and end of the tunnels, regardless, yeah?
You are talking about this, right? Yes.
Regardless.
That would be the that would be the tunnel end.
If you have like 100 logical hops in between here,
yes.
Just only
one.
Only one, which is the physical network card,
right.
Which start of the tunnel and end of the tunnel.
Right. Correct. So based on your question, let me ask a question for everybody. Now I have only 2 customers in here. Let's assuming that I have 200 different customers over there, 200 different customers over there. How many tunnels should be built?
Technically one.
Only one tunnel.
One tunnel.
All
so
the
when we
central-
talk about the tunnel, as long as the source and the destination the same, the tunnel is one tunnel. But how you identify the traffic between the 200 customers and the other 200 customers? Based on the label.
Yeah, but if you're doing MPLS over GRE, it's gonna be another label in the MPLS cloud.
And this is MPLS over GRE. This is MPLS over GRE.
No, I mean like the tunnel going through different MPLS cloud. Different MPLS cloud.
Oh yes.
I just want to see that.
So you will see.
That will be another story. Yes, we have another slide talking about that.
Okay.
Yeah. That will be this slide.
Ah.
Yes, layer 3 PTN. That's
Yes. Let me finish up 2 more slides, then we can have a short break. Now, if you can see this is a compute node in data center 1. So data center 1 has a controller. This is the controller. This is compute node in another data center. So there is another controller over there, data center 2. And the data center, before you leaving the data center, each of the data center has a gateway.
Yes.
There's a gateway. After you leaving the data center, you will have to go through probably the third-party MPLS network.
Yes.
So I would like to draw the network like this, partitioning. This from here, yeah, should be this. This is data center 1, right? And this from here. This is data center 2. And this in the middle, that is the WAN.
Yes.
Now this time, something interesting. Again, VNB just spin up. So VNB got an IP address from the DHCP server, which is 10.1.1.2. So in that case, there is a directly connected route automatically generated, which is not shown here. But we know the V router will exchange the route to the data center controller because this is control. So by using what? By using XMPP, okay, sending to here. So let's focus in the controller. When the controller receiving this, the controller say, all right, I have received 10.1.1.2. So where I received that route? I received the route from the compute node in here with an IP address of 192.168.10.1. So the next hop is this, right? And since they sending the route already generate the label 17. Now here, we also come with the RD and RT. RD is route distinguished and RT is route target, which means we are going to use the MPLS VPN. So the controller will sending the route to the gateway. Now, since these two devices are in the same data center, so between them, they are running the BGP, but it's IBGP. Because the AS number is the same. Since their AS number is the same, so when the controller 2 sending the route to the gateway 2, the next hop still 192. Because IBGP won't change the next hop by default. However, when the gateway 2 receives the route, now gateway 2 want to exchange the route to service provider or the WAN by using eBGP. So the gateway by default will change the next hop to itself. That is 10.160.20.1. And however, the label will be changed because we need to swap the label. And then the route will send into the P2. Then P2 will send in the route to P1. Probably internal goes through the route reflector. But I know since this is IBGP, so the next hop will be the P2 itself. And then sending the next hop to here. Now P1 receiving that route, it will see that label has been changed again because label swapping. And then P1 will sending the route to gateway 1. Since this is eBGP, so the next hop will be changed to P1 itself. 10.200.1.1. And then by receiving the route, the gateway 1 will sending the route to the controller by using the IBGP. Now here, PE1 sending the route to gateway 1 because it's eBGP, so the route in here next up is this guy. But since this is the gateway sending to internal by using the IBGP, so normally by default, the next hop should not be changed, right? But in order to let your internal device to be able to resolve the next hop, so you will probably do something like next hop self. So you change it to next hop self. So you see the route sending to this guy, next hop is changed to 10.80.20.1 is the gateway in here. Okay, and then it's a route reflector. So the route reflector will reflect the route to the compute one. Now, when the route sending to the compute one, I have a question for everybody. When the compute one receive the route, compute one will see the next hop, which is the next hop. Next hop to controller DC1 or gateway 1 or PE1.
Gateway. Yeah.
Gateway 1, right? Because we just mentioned about gateway to next hop self.
Yeah.
So you send the route to here, you will see the next hop is gateway 1. So in that case, if the BMA want to forward the traffic to BMB based on the route will sending the traffic to the tunnel. So please tell me, where is the tunnel end? Yes, gateway 1. Because you see the next hop is gateway 1's IP address. So same thing, if the BMB want to send the traffic to BMA, so the route will in the reverse way sending to here, but you will see the route, the next hop is your gateway 2. So which means you will build up the tunnel from here to gateway 2.
All the way to the
So which means in this case, the tunnel is not passing through. Okay, tunnel is ending in your edge of your data center. So when the traffic sending from here, from the BMA1, internally, the label will be put into the packet with the label of 417. So when the traffic all the way comes to the gateway 1 by receiving the 417, and because the gateway 1 has the MPLS label swapping table, so the MPLS the traffic will be retrieved from the gateway 1. And by looking at the label, which is label 417, it will based on the swap to 217, and forward to the PE router. Then the PE router just do the LSP. The LSP will forward the traffic all the way to the PE2, eventually becoming 217, and 217 sending to here will becoming 117, and then getting to the tunnel again, eventually reach out to the destination. Okay, this is only one of the ways how you connect the data center together. Not always like this. It's only a case. In this case, we called it layer 3 VPN.
Where's the mapping between label 417 and label 17? Is it in LS label table in B1, BE1?
Your question is, where is the mapping between 417 and which one?
And
label 17.
Label 17.
must be mapping somewhere.
No, that's hot. Yeah.
No, it's not.
Yeah.
Which one?
It
Which
is.
one?
He's asking where this goes to 17.
Oh, goes to 17. Oh.
But this gets changed here, and then that gets changed there and then.
Yeah. Because when you send the route, you initially send the route, you generate the label in here is 17, right?
And then that gets
And
changed.
you go to here and it will receive the route with 17. Sending to the gateway will exchange route. Now starting from here, it's already MPLS. So it will generate this one.
Yes, so in this table, we map 17 to 117 and then move to the next hub, move to the next hub.
Yeah.
Right. That mapping.
Right.
To go.
Correct. Yes.
Okay.
One more. And this is the layer 2 overlay. But now, this is actually easy. But I don't want to go through this. I only want to ask you a question. Whenever you say layer 3 tunnel and the layer 2 tunnel, what's that mean? What's different between layer 3 and the layer 2? They are all tunnels, right? But why you say that is layer 3 tunnel?
Layer 3 passes to routers.
Layer 3 passes to the router.
Layer 2 tunnel through any WAN protocol. This is MPLS, layer 2.5.
If you talk about the layer 3, there's a tunnel. You say that, oh, that is layer 2 tunnel. It allows you to send in a traffic, and the traffic is a Ethernet header. Okay, and we just care about the MAC address. We don't care about the IP address. So which means the traffic will sending all the way to here, just like you are directly connected. So both of the sides can use the same subnet. But just like you said, layer 3 goes through the router. So if you build up the tunnel, that is layer 3, then the traffic sending to here. Now this time, instead of look at the MAC address, I'm more focused on the IP. So I need to base on the destination of the IP to see which tunnel to go. So which means I need to check with a routing table, right? And then based on the routing table, send to the tunnel. And then the other router receive it based on the route IP header and send to the correct interface. So in that case, the left side, probably 10.1, the right side should be another subnet, probably 20.1. So we call it layer 3 tunnel. Internally, the traffic need to be routing. Internally, the traffic need to be switching. So that's the difference. Okay, so we have different tunnels. Let me put that again. MPLS over GIE, MPLS over UDP, and the VXLAN. If you use the MPLS over something, then you can identify the customer traffic by using the MPLS label. If you are using VXLAN, then you can identify the traffic by using the VXLAN VNI. How many labels in a single MPLS header? MPLS header, how many labels? How many bits? How many bits? 12? No. 16. 20. Ah, okay. How many bits in the VNI? 24. Who wins? VXLAN wins. Okay. Now there's another one. Now if I have a traffic, the traffic is a tunnel traffic. Now this is VXLAN. VXLAN will be encapsulated internally. They will encapsulate with a UDP. So if the traffic reach out to a device, a switch, now the switch has multiple connections. Now the switch will do the load balancing because the switch has multiple connections from the spine to the leaf. Okay. Now in the switch, normally if you would like to do the load balancing, this traffic will has to be sending to a hash function, the hash function. And sending to the hash function will hash some of the information from this header, from that header, from that header. And then after calculate the hash value, based on the hash value, we can decide, oh, go this way, go that way, go that way. So which means if you have multiple traffic comes to here, if they have different IP, different port, different VMI number, you can do load balancing very precisely. But if we're talking about the tunnel is MPLS over GIE. So MPLS in the previous slide, we have GIE, we have IP. Again, you would like to put this traffic to one of the link over there, but you have to send to the hash function to calculate the hash value. But in this case, you can only see the IP address. Here is also the IP address. I didn't put it in here. This guy has the IP address. This guy has the IP address. But this guy has the port number. This guy don't have the port number, right? So which means as long as you are using different IP address, you will be able to load balancing to different paths. But if you are using same IP address in here, then you will always go to the same path. you will always go to the same place because when after you send into the hash, the value was always the same. So from load balancing point of view, who will more precisely be load balanced by the layer 2 device? VXLAN. Why? VXLAN has the port. MPLS over GIE no doesn't have the port. So MPLS GIE load balancing is not so good. So who wins?
VXLAN.
VXLAN wins again. Okay. So if you put that everything together to comparing to each other, you will imagine that everybody loves VXLAN nowadays. So you need to learn about VXLAN. That's why. Okay. So let me pause in here. Any question from you?
Can I go to the previous slide, the one that
Previous
you
one?
edited?
Yep.
Yeah, this one. Hold on.
You want to take this?
Yeah.
Okay.
And the previous one? Yeah. You edited the.
Well, it's gone.
Oh, it's gone. Okay, that's all right. I have to.
All right. So how about let's break it here? Lunch break. Now afternoon, I would like to start the training at 1:40. Is that okay? Okay. Thank you. 1:40. 1:40.